In this example of a combined loading problem, we actually have a very simple system and very real, but even the simplest and realist of systems or situations can turn into having a lot of little complexities here, and we'll see that as we go along. At the same time, it is a great review of all the basic principles that we've been developing and learning throughout this term. Right? So what we have is just a C clamp, and we're trying to figure out what the allowable clamping force is associated with this thing. The material that's used in the clamp itself has a yield strength of 324 megapascals. That's a yield strength that is true in both tension and compression. And we have a desired factor of safety of 3, which is on the high side if you're talking about a building kind of situation, but for products such as a clamp and ways that people might use or misuse the clamp, that's maybe not so unreasonable to have a higher factor of safety associated with it, right? So you see the cross section there of the clamp, and the particular part that we're going to focus on is this T shape, and we're going to go take a look here and see what we can find out about the allowable clamping force. So we've got some basics of the problem restated here. Here's our clamping force. There's the C part of the clamp. And a critical distance here is the 40 millimeters from the centroidal axis of the clamping force down to the top of this cross section. So that's the top of this T. The T is 16 millimeters high. The stem is 4 millimeters wide, whereas this flange is 12 millimeters wide. Right, and again, here's our yield strength and our desired factor of safety, and we're going to go find out what that allowable force is. So we're going to just report what some of the preliminary work is, and that way you can have a little bit of a review opportunity to go back and see if you can confirm how that all works out. But we're going to need to find the centroid of this cross section, and when we do that, we'll find out that the area is 96 square millimeters along the way, right? Well, that's an easy one. 4 times 12 for that rectangle plus 4 times 12 of that rectangle, that's 48 in each, so that's where our 96 is, right? But when you go find the white bar, what you're going to find out is that from the top, it is 6 millimeters, right? So the centroid of this cross section, geometric centroid, then is located here at 6 from the top, and then 10 millimeters from the bottom. Right, then we're going to go apply the parallel axis theorem and find our second moment of area with respect to our bending axis, and that is 2,176 millimeters to the 4th. There's nothing obvious about that answer. You have to go perform the appropriate calculation to get there. Right, so now let's look at the statics of the situation. And when we go look at this cross section, then there's the top of it, there's the bottom of this portion there, and there's that part. And when we go do the free body diagram, let's do that real quickly up here. There's your compressive force at the top from the clamping. So that means we're going to have for equilibrium down here at this location, right through the centroid, we're going to have then the same force P. And then we're going to have well, this is a force couple, right? That it's tending to want to spin this in a counterclockwise fashion. So we'll have to have a restoring moment, M, that is opposite of that, and that's going to be equal to P times the eccentricity. Now the eccentricity here is got a little wrinkle in it, and that is because it's not the 40 millimeters, it is the 40 millimeters only takes us to the top of the section. We got to go down to the centroid, and that's then another 6. So the eccentricity is 46 millimeters. Right? So there's your two sets of internal unknowns. And from those, then we have our stress model. One for each of these, right? And although we could just write out the formula, what I want to do instead is show the stress diagram that goes with each of these. And that's to emphasize what's happening here. And so there's our axial, and that axial would be equal to, of course, P over A. And in this case, that would be P equal to, or rather P over our 96 square millimeters. Now the stress distribution that comes from the bending moment is going to be sigma equals my over I. Now, with the way the moment is set up here, we're going to have tension on the top, and we'll have compression on the bottom. The neutral axis is closer to the top, so the top stress is actually smaller. Right? And so the net effect of those, well, let's get that model in first. Sigma bending would equal then my over I. So now we have to decide which is going to be the worst of these two. And you have to decide, is the combination here at the top going to be a lot worse than here at the bottom? I would tend to think it's going to be dominated here at the top, tension and tension, but it's all about the two magnitudes here, about which is going to be the total worst effect. So I'm going to go look at the top. And see, and for that, what we might do is we'll call that H for the top and capital B for the bottom. We might have to do both, to be honest. We'll have to see here. So let's look at sigma H. That's going to be P over A plus the M, which is P times E times that distance to the top is 6 millimeters over our I value, right? And numerically then, that's P over 96 square millimeters plus P times our 46 millimeters times our 6 millimeters divided by our 2176 millimeters to the fourth. Right? Now, our sigma down at the bottom is going to be a tensile P over 96 square millimeters plus our P times our eccentricity of 46 millimeters. And then we've got our, it's no longer 6 to the bottom from the neutral axis down, it's now 10 millimeters over the I. And I hope you're seeing that I made a potential mistake here. This is a compression, so we need to have that be negative, right? And I think, what are we going to have here? 2176 divided by 460 is 4.73. That's a smaller number here in the numerator, the effective numerator, which means really the compression is going to overwhelm this value. Let's see, that's the same. Well, it's not the same at all. Still not, still a little hard to see what's going to happen here. So let's work it out just one more step further. sigma h, and let's make a common denominator kind of thing going on here, right? So we've got 2176 divided by 46 divided by 6 is 7.88. Yep, 7.88. And so that would be P over 96 plus P over 7.884. And then what we'll do is we'll find out what that equals, plus then 6 reciprocal equals that. Take the reciprocal of that. I'm just casting this in terms of this denominator, so I have a feeling for how big this number is going to be, 7.286-ish, right? Do the same thing with sigma b, and just draw a line between those that help keep them separated. And we've got P over 96, and then this 2176 divided by 460 is 4.73. And we get a negative. Did I do that right? I don't think I did. 96 minus 46 times 10 divided by 2176. Yeah, I didn't do that right. So that would be minus P over a 4.976. Right now, this is actually the smaller stress, isn't it? It's going to be compression that's going to control this, interestingly. Not sure I like that conclusion. It's happening because of bigger moment arm is what is going on there, and that's why that's happening. So this is actually the larger absolute value. We're controlled by compression. And so now our allowable stress is pretty easy to go find. Right? Sigma allowable has to be smaller than the yield. And so that's our 324 megapascal divided by our factor safety of 3. That's going to be 108 megapascal. And now we can find our allowable load. Right, and so we just have to solve these two. And so down here at B, then what we do is set our sigma B equal to sigma allow and solve for P, right? And so that would be P equal to 108 megapascals times our 4.976 square millimeters. Where the square millimeters come from? Millimeters squared over that, right? That's where those units are sitting. And so megapascals is the same thing as newtons over square millimeter, so they cross out. So this, oops, right, so that times the 108, and we get 537 newtons for that one. Now, if you want to check the other one for fun, and we'll find out that P equals the 108 megapascals times the 7.286, and of course 7.286 times 108 is the bigger number, and we need the smaller number. So that's our answer. Now you might say, you might be thinking ahead, but wait a minute, what about more circle? Right, so the little stress block that we have down there at the bottom has got then a net stress at B of 530, oops, I don't know what the net stress is. What is it? Well, we set it equal to 108 megapascals. Right, and so it's a uniaxial condition, so that max normal stress really is that value right there, right? That our Morse circle that would go with that would be, quite simply, one that looked like that. Might be tangent to the curve, and there's your 108 right there. Whew, it's a lot of work, isn't it? Not too bad, but there's a lot going on there.